All right, it's 2:30. We're going to go ahead and get started. This is week 4 of Advanced Kentucky's online content review sessions for AP Calculus BC. My name is Aaron Timmons. I'm the Mathematics Content Director for Advanced Kentucky. I'm joined today by current AP exam reader Michael Marshall, who's also our Access to Algebra Content Manager, and our presenter for today, Mr. Mark Howell. A couple quick housekeeping items, and then we'll get started. So this review session, we are intending for Kentucky audiences. However, we know there's lots of teachers, students from across the nation. Welcome. We will do everything we can to make this an equitable opportunity to learn. During the session, we really encourage participation, but we know that any participant that is causing a disruption will be removed. So please be aware of that. Contact information is on that screen right there. Feel free to give us a follow. If you have questions that you'd like to ask after the session, feel free to shoot us an email. We'll get right back to you. Your microphones will be off for the entire session. Along with your video, please turn your videos off. And we really encourage you to use the chat feature on Zoom. So the bottom right corner, please make sure you are asking questions. Michael and I will be monitoring the chat for any questions that you may have, teacher or student, so please ask away. Also, if you notice on the participant screen, there are some buttons for yes, no. We'll be utilizing those potentially, so make sure you can use those. All you gotta do is hit the button and your response will be recorded. So we want as much participation as possible. KYAP2020.com is the site to go to see recordings of today's session as well as any other ones. There's also other resources on there as well, so please make sure you're checking out that website. So we're going to take about 2 minutes here to let you get situated. Make sure you have today's handouts in front of you. And also, if you can open up another browser and go to that bit.ly link and sign in for us, we would appreciate it. It's a very quick 4 or 5 question Google form. I'm going to pause the recording, let you get everything you need in front of you. We'll resume here in about 2 minutes. All right, hopefully you've had enough time to get what you need in front of you. Please go ahead and put in the chat where you're from. If you're a teacher or student, we'd like to have a good idea there. Welcome you to today's session. So I'm going to turn things over right now to our presenter, Mark Howell, who can give us a little bit of background of where he's coming from, give us some AP Calculus background as well. So Mark, without further ado, it's all yours.
Thanks a lot, Aaron and Michael. It's good to be with you all today. I'm sitting in my beach house here in Delaware and spent my day working with my own students at my alma mater, a school that I went to myself in Washington, D.C., Gonzaga High School, a Jesuit school. It's been a great place for me to work. Some of my own students are joining us here today at session. Our session A is on free response strategies and mixed review, I think is the title for Calculus BC. So let me start by sharing my presentation with you. I want to run through first, there's just several points, and most of the stuff that you're going to see on these slides, most of the stuff that's on the slides, I think you'll also see is in the handouts. And the teachers that are here will have access to solutions to the problems that are in the handouts. There's certainly going to be more stuff in the handouts that will have a lot more in the handout that we'll have time to go through today during this 1-hour session. But feel free, afterwards to work through those problems. My thing was to try to give you problems that I think will be at least in their flavor in the parts of the problems that I've given you, similar to what you're going to see when you take the AP exam on either May the 12th, or I think the other date is June the 1st. In fact, I think I have that one on one of these slides. So at any rate, logistics and format for the exam. The exam is going to consist of course, 2 free response problems. The first being 25 minutes with 5 minutes after that to upload the response, and it's going to count for 60% of your score on the exam. That will be immediately followed by a 15-minute question with 5 minutes to upload that response, with that being weighted 40% of your score. Each question will include topics from 2 or more units. The exam will be open book and open notes. You'll be allowed to use your calculator, but no question will require the use of your calculator. And there's a link here that's also in your handout that will have more information about how to go about preparing yourself for an exam that you know is going to be open notes and open calculator. In fact, the fact that it's open calculator shows you that if you're using your calculator, you're probably chances are really good that you're wasting your time. There's not going to be any question that's going to require the use of the calculator. So I guess it's next week, actually, a week from today, starting a week from today, Monday through Friday at 9 o'clock Eastern time, there will be some review sessions focused on constructing and submitting responses to free response problems in the format that is likely to appear on the exam. This week, there are also YouTube review sessions every day, Monday through Friday, starting at 9 o'clock, lasting for 1 hour. Those sessions are also recorded. And so you can look at them either live or you can look at them in the recorded format. Having the time to practice actually doing an exam question and in the time period that's framed is obviously, I hope, to you good practice to prepare for the actual exam date. I was going to mention that, you know, there are these two separate questions. You don't have the total time to work on both questions and then submit both at the end. No, you have to work the first problem, finish it, submit it, and then we'll work the second problem, finish it, and submit it. That is, there's dedicated times when you upload your response to each question separately. So what about the two problems? What do we know about trying to psych out what these questions might be asking? Well, I think this first point that I'm making here is an important point and may be overlooked by a lot of people. These problems are going to be like past problems that you've seen on past exams. It's not like anybody's going to reinvent the wheel in these two questions. As I mentioned, they will be calculator neutral. There will be little, if any, problems that will require you to find derivatives or antiderivatives of known functions. By known functions, I mean functions like x squared over 1 plus x cubed, or the sine of e to the 3x, things like that. You're not going to be asked to differentiate or integrate functions like that. And the reason is that the questions have to be calculator neutral. Some students are going to have available to them computer algebra systems which would answer questions like that flawlessly, but some students won't have such a calculator. So you couldn't have problems on a test and have a fair test where some students have an advantage over others because they hold this machine that can produce the answer for them. It's likely, as a consequence of that, that when functions are presented to you, they're going to be presented in really one of three forms. They're going to be presented graphically or numerically, but you can also define other functions symbolically as general functions in terms of a function that's presented graphically or numerically. So they might give you a table for like f of x, and then define some other function g that would be f of, say, x squared plus 1. And they could ask you questions about f of x squared plus 1. And so that means that you can test things like the product rule or the chain rule, just not with a specific function, but with a general function. And I also will point out that I think that they went through all that trouble to leave series in the available content to test upon. That is, it's from unit 10, but they omitted the material from another unit on parametric and polar functions. And what that means is that they wanted to have a question about series. At least it means that to me. And so I think it's likely that you're going to see at least a part of a problem that's going to involve infinite series or Taylor polynomials. Because it's an open book test, it's likely that the test is going to be highly conceptual in nature and not procedural. That is, there won't be problems where you can kind of turn a crank and spout out a response. You're going to have to think. You're going to have to explain things. You're going to have to interpret what something means. Here's this derivative. Tell me what it means. Here's this integral. Tell me what it means. They're going to ask you to justify why something is true. How do you know that there's a point of inflection on the graph of this function? How do we know that the first degree Taylor polynomial underestimates this, this function near this point? You're likely to have to apply theorems, definitions, or test in specific situations, and then explain reasoning that's behind those applications, perhaps. But these are the kinds of things that I think you want to focus on, not things that are just sort of turn the crank, such as, say, given a symbolic differential equation, solve the differential equation by finding antiderivatives of known functions. You can't ask those questions on this exam, and the reason is because, again, some students have machines that'll answer them, or computers, for that matter, that'll answer those kinds of questions. So the problems aren't going to be subject to typing the question into Google and finding the answer. So what about explanations and justifications? So given that we're likely to see those kinds of questions, what are the proper explanations and justifications that you're likely to see? So I decided that it would be a good thing to put the sort of minimalist correct justifications for the most common kinds of justifications and explanations that we've seen in the past. And so that's what you're going to see on these next few slides. Okay, so here's a justifications for relative max or min. A function f has a relative max at x equals a because f prime changes sign from plus to minus. And you'll notice I'm trying to be very concise here. So notice my reference there to f prime. I didn't say because the derivative. I didn't say because the graph. I didn't say because it changes sign from plus to minus. Writing f prime is a specific name. Referring to mathematical objects by name when you're writing justifications is really important, okay? Increasing and decreasing, the best kind of description or justification or explanation for why that might be true would be something like f is increasing on a certain interval. Usually that's how they ask those questions, because the derivative is greater than or equal to 0 on that interval, or just there. And then for concavity, a function graph is concave up on a certain interval because the derivative is positive on that interval. Now there's other justifications for concavity that would be acceptable, and I've included those in your handouts. For example, that the first derivative is increasing, f prime is increasing, meaning the second derivative would have to be positive. And by the way, each one of these also has a vice versa side to it too, right? Like concave down because the second derivative is negative, or decreasing because the first derivative is negative, or relative min because prime changes from minus to plus. Points of inflection. Again, there's a couple of ways to justify a point of inflection. I've pointed out one right here because the second derivative changes sign. Notice it's not because the second derivative is 0. And it's the unique change in sign in the second derivative. It's not because the second derivative doesn't exist. Those can be places where it's possible you have a point of inflection, but just because you have a 0 in second derivative doesn't mean you have a point of inflection. And then finally, as far as these kinds of things are concerned, continuity and differentiability. Knowing these definitions, or at least having these things written out in a good form in your notes, is an important thing to have. So if I were a student preparing for this, I would have these definitions written down, because I may need to refer to these definitions, and I don't want to have to look in my book or to Google to find these things. I'd like to have these things arranged in a very tight sort of place as I sit to take this exam. So here's the definition of continuity, and here's the definition of differentiability. And in your handout, I go through, I think, an example to explain exactly how you would apply this definition if you had to justify that a function was continuous, or if you had to justify that a function was differentiable at a point. I do want to point out something about this thing. There has been in the past, there was a question on a recent AP exam where the question asked, is a function differentiable on a certain interval, or at a certain point in the interval, and justify your answer or explain your reasoning, something like that. And the acceptable answers that year on that exam were things like, the graph of the function has a corner point, therefore the derivative doesn't exist at that point where there's a corner. It took all sorts of sort of colloquial expressions, common English expressions, to describe why. And in my mind, if we wanted to test whether a student knows what differentiability really means, I think we should be testing it by asking what the definition of derivative is, what the definition of differentiability is. And many people miss this point, that the definition of derivative at a point is also the definition of differentiability at a point. That is, both of those terms, the derivative at a point and the differentiable at a point, are defined in the same definition. So when is a function differentiable at x equals a? It's when these two one-sided difference quotient limits are equal to one another. And what they are, that number that they are, that is equal, that is called the derivative. In other words, this thing right here is equal to, this thing is equal to f prime of a. That is f prime of a. It is what those two one-sided limits is. And so, so because of that, I think that if we were going to ask a question that assessed whether students know what it means to say something is a function is differentiable at a point, that's the way to ask the question. Force the issue by saying, use the definition of derivative to show whether f is differentiable or not at that point. Okay, I'll get off that soapbox and move on to the next thing. What other kind of things might you ask to be explained or justified? Convergence or divergence of a series. So the answers to a question, does this series converge, diverge, point, will be one of 4 answers. And those 4 answers rely upon the 4 tests for convergence of a series that are described in the handout that we talked about at one of these previous sessions on infinite series. Either the ratio test, the alternating series test, the geometric series test, or the p-series test. Those are the only tests that are open to be assessed on this exam. So one of those 4 is going to be the one that you're going to use if they ask you for convergence or divergence of a series. So what do you have to have in front of you? What are the hypotheses? What are the conditions that are met in those tests? And those conditions are described in this other handout that was on the infinite series session. So I hope that that handout is available to and easy to access, Aaron, for the people that are at this session, as well as the folks that were at our series session.
They are.
The other kind of questions that you might kind of see or that have that have appeared in the past on past AP exams are functions that are questions that ask you whether or not a function input exists in a certain interval with a certain property. Is there a number c in this interval where f prime of c is equal to 2? Is there an input to this function equals a such that f of a is equal to 0 in this interval anyplace? So whenever you see a question like that, you can be 100% sure that that question is asking you about one of the 3 value theorems that appear in AP calculus: the intermediate value theorem, extreme value theorem, or the mean value theorem. Why can you be sure? Because those are the only theorems in AP calculus that guarantee the existence of a number in an interval. So when you hear a question that asks, is there a number in a certain interval with a certain property, it's going to be about one of these value theorems, either intermediate, extreme, or mean value theorem. Okay, so now on to interpretation. So if you're an AB student, if you happen to be an AB student, then you're not worried about these kinds of questions when they refer to an integral, but you will be worried about these that I describe on this slide that refer to the derivative. So you may be asked to interpret the meaning of derivative in context. And they'll usually ask you to use correct units to do that. So how do I find the units on a derivative? They're always the units on the function output divided by the units on the function input. And that previous slide you saw where I was talking about differentiability explains to you why that is, because the function values are in the numerator of that difference quotient, and the inputs to the function are in the denominator of that difference quotient, and it's the limit of that difference quotient that is the value of the derivative. And so by golly, the units have to be the units in the numerator divided by the units in the denominator of that definition, meaning the units on the function output divided by the units on the function input. Your description of the meaning of a derivative should always say something about a rate of change. It's the rate of change of the function with respect to the independent variable. Just use the words from the stem of the problem to figure out what the the meaning of the function is. Don't try to make it up yourself. They have to tell you what the function, if this is a contextual problem, the stem of the problem has to tell you what the function is. And they always do. Just look at past problems. I'm 100% sure you'll see that every one of those problems describes what the function is in the stem of the problem. It would be smart to get in the habit of looking to the stem of the problem in order to describe that, and then just rate in front of what it says about what the function is. And then make sure you mention units on the derivative and units on the function input. And make that you mention units on the input is going to force you to mention the value of the input. And I think we'll see an example of that in just 1 second. Here we go. Here's an example of a contextual interpretation that came from the 2018 international exam. We have this table of values for g of t. What's the meaning of g of t? Well, they got to tell you someplace. G of t is the rate at which grain is being added. And when you see the word modeled by the differentiable function g, you could just interpret that to mean is g. The rate at which grain is being added is g, and g happens to be differentiable. And what are the units on g? G's units are cubic feet per minute. This is what I meant about looking to the stem of the problem for the meaning of the function, okay? And of course, t is the input to this, and what are the units on t? It's given in the table. T is measured in minutes. Using the data in the table, approximate g prime of 3, and then interpret the meaning of prime of 3 in context. So if you're going to do an approximation of g prime of 3, you got to look to the table and see which interval 3 is in. It's this interval from 1 to 5, and we're going to write down g of 5 minus g of 1 over 5 minus 1. And then that won't give you the approximation yet. You have to pull the values out of the table. Sorry. Here we go. So g of 5 is 20.5 minus 15.1 divided by 4. By the way, this answer right here would be sufficient for that approximation. You don't need to do the arithmetic there. You don't need a calculator to get an answer here. That's perfectly fine. You should attach units to this, or you could attach units in your justification. If you have them in one place, you don't have to put them in the other. The units on this thing will be the units in the numerator, which are given right there. This is cubic feet per minute. So I would write cubic feet per minute in the numerator, divided by, and in the 4, that's 5 minus 1, that's values of t. T is measured in minutes, divided by 4 minutes. And now I've got the units, cubic feet per minute. And what does it mean? Well, this is going to be some number, okay? And it looks like it's going to be a positive number. And so I would say that the rate at which the grain is being added is increasing at the rate of this thing, cubic feet per minute at t equals, or approximately at t equals 3 minutes. And so notice I put the 3 minutes, I put the minutes on the 3, and I put the units on this rate of change, the rate of change of a rate of change, okay? So I find the problems where you have to interpret the rate of change of something that's already a rate of change can be confusing for students, but if you approach it the way I'm trying to emphasize here, I think you can keep your head on straight. Okay, so what about if you're asked to interpret an integral? And this is the kind that the AB students don't have to worry about. So in an integral, the units are always units of the function output multiplied by units on the function input. And notice how that compares to the previous example where in the derivative it's divided by units of input. Integrals and derivatives, in some sense, by the fundamental theorem, are sort of inverse processes of one another. So it shouldn't be surprising that all I had to do was replace the word divided with multiplied here in this sentence. So we multiply units on the output by the units on the input. And if you think about the way an integral is set up, the integral of f of x times dx, that's the function output times dx, the function input. When you integrate the rate of change of something over an interval, the result is always the net change of that thing over the interval. That is the interpretation. The integral of a rate of change gives you the change. Again, use words from the stem, okay, to do that. And again, I would urge you, emphasize the units on both variables. So if you have an integral to interpret, make sure you mention the units on the independent variable. That'll get you talking about the interval over which you're integrating. And you need to include both of those things, the meaning of the output, the value of the integral, and when, that is the interval of the domain of the independent variable where that integral is being computed. Make sure you know how to recognize average value as an integral. So there have been problems in the past where you had an integral like of 1/8 times the integral from 2 to 10 of some function, and that would average value of that function over the interval from 2 to 10. Recognizing volume, area, and arc length setups is an important thing to do. I make sure I had all of those sort of laid out right in front of me as I was getting ready for the exam in my notes. We'll move on to the next slide as soon as I find it. Okay. Let's see. So here's a contextual interpretation and units example using an integral involving a parking lot. This is from the 2019 international practice exam. So again, we have a table of values. Notice the presentation of the function in a table instead of as a symbolic definition. Okay, and that's been the case for these interpretation problems, either a graph or a table. So we have the rate at which the cars leave a parking lot modified by the differentiable function L. Here's some values of L in the table. Time is in hours since 5 a.m. t equals 0. Use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate this integral from 2 to 12 of L of t. Using correct units, explain the meaning of that integral in the context of the problem. So I'm not going to go through the computations of the trapezoidal sum. Those appear again in the solution to this problem that's your teacher will have. But the interpretation is what I want to focus on. So explain, using correct units, explain the meaning of this integral in context of the problem. So we have the integral from 2 to 12 of L of t, and L is the rate which cars leave a parking lot. So it is a rate of change. The integral of a rate of change is net change. Net change of the thing whose rate we knew, which are cars. We know the rate at which cars are going out of this parking lot. So this is going to be the change in the number of cars in the parking lot. Okay, so it'll be, in fact, the change in the number of cars in the parking lot from t equals 2 until t equals 12, which I guess is from 7 a.m. until what is it, 10 hours after 7 a.m., whatever that is. Is that 5 p.m., I think? Did that right. So use the terms from the, so you make sure you use the terms from the stem of the problem. They give me the rate at which cars leave a parking lot. So this will be the number of cars that have left the parking lot. Okay. Over the time interval, t equals 2 to t equals 12 hours. And you wouldn't have to interpret it as time of day necessarily. If you said from t equals 2 to t equals 12 hours, that would be fine. Or hours since 5 a.m. would be even better. That would be fine. Okay. So how are we doing so far? We're going to get ready to take a look at a specific problem. I have a sample problem that actually I have 4 sample problems, 3 of which I wrote. I want to go through in detail the first one and then give some time to look at least parts maybe of the other 3 problems. Okay. So I hope that the pace is okay with you now and that you're all on board, ready to look at another problem. If you need me to slow down as I'm going through this or speed up, I get it. Then you can indicate those with those icons, I think, that you can enter into the chat. Okay. So here's a problem that I adapted from this book that I co-authored with a friend of mine, Martha Montgomery. There's a graph of a function h of x that's shown that consists of 3 line segments that you can see and 2 quarter circles. And this is a common kind of ploy on exam questions, because you can use geometry to calculate areas in a problem like this, okay? And each of these circles is given to have a radius of 5, okay? Then they define this function g by g of x is x plus the integral from 5 to x of h of t dt, where h is this function that's grasped up above, and g has a domain of x equals -7 to x equals 9, just like the function h's domain. So part A, write an equation for a tangent line to the graph of g at x equals 6. So we need 2 things for a tangent line. We need g of 6, and we need g prime of 6. So how do I find g of 6? Well, I substitute x equals 6 in the formula for g. It's 6 plus the integral from 5 to 6 of h of t dt. I look up here at my graph of h. I need to integrate h from 5 to 6, and I notice that the graph is linear and below the x-axis. So I need the area of that little triangle, and then realizing that I'm integrating a function that's below the x-axis, I'm going to get a negative value for that integral. So this is going to be 6 minus 1/2, or I could write that 5.5. G prime of 6, well, I need to find g prime of x to get g prime of 6. G prime of x can be computed by differentiating the sum and getting 1, and now the fundamental theorem comes to the rescue to differentiate this function defined by an integral. So it's 1 plus just h of x. So you got to know the fundamental theorem. You got to know how to differentiate a function defined by an integral to have any chance at all on a problem like this. So g prime of 6 is 1 plus h of 6, and I can get h of 6 by reading off the graph. It's the y coordinate of that point that I've highlighted, and that looks like -1. And so this is going to be, sorry, this is supposed to be an 8. So 1 minus 1, oh my goodness, that's 0. So the slope of this tangent line is 0, and the y coordinate on the tangent line is 5.5. Is it possible to write an equation for a tangent line that's horizontal? Well, yes, it is. The y's on a horizontal line are all constants, and since one of them has to be 5.5, all of them have to be 5.5. So the tangent line has equation y equals 5.5. Okay. So let me move down to the next part of this problem. Find the x coordinate of each local maximum for g and justify. So sorry about having to scroll up and down on you. If I want a maximum on the graph of g, I got to know where g prime changes sign from positive to negative. I'm not looking at a graph of g prime. I'm looking at a graph of h, and g prime is 1 plus h. So what I have to imagine is this graph, this red graph you're looking at, being lifted up 1 unit. And one way to visualize that is to think of the x-axis being dropped down 1 unit. So I'm going to sort of draw a temporary x-axis that's 1 unit below the existing x-axis. And now I want, that's the x-axis. That would be the x-axis for the graph of g prime of x. So now I need the red graph to change sign from positive to negative through my dotted x-axis, my new x-axis, okay? And it looks like it happens right here at x. I should do this. I should have done this in a different color. Right here at x equals 6, okay? It looks like g prime is going to change sign from positive to negative there. So I would answer x equals 6 because g prime changes from, I'm not going to write the word out, positive to negative, because I want to get as much stuff done as fast as I can. I'm going to write positive to negative, and that's all I need. Typically, I would write there, but I have room there to write there. Okay. So next, which is larger, g of -6 or g of -5? Give a reason. Well, I think it's really easy to get confused on a question like this because you might be tempted to think about answering this question by think about accumulation of area. But if you look at my graph of g prime, which is the one, you know, where we have this sort of imaginary x-axis, 1 plus h. 1 plus h is the graph on with the x-axis being the dotted line. There's a graph of 1 plus h, and notice that on the interval from -6 to 5, this interval here from -6 to -5, notice that g prime, this piece of the graph right here, is 1 unit above, or well, it's between 0 and 1 units above the x-axis. It's definitely above this other x-axis that was 1 unit below the other one. And so since g prime is positive on that whole interval, the biggest value of g will be at the right point. And that's the answer to this question. So you would write for the answer here, g of -5 is larger because g prime is greater than 0 on the interval -6 to -5. You don't have to put the words interval in there, okay? So if you have any question about any of that, please type it into the chat, and either Aaron or Michael is going to give me a high sign to address that. Otherwise, we're going to move on to the next part. Which asks for the x-coordinate of each point of inflection on the graph of g, and give a reason for your answer. So a point of inflection on a graph of a function occurs at a place where the derivative changes sign, or where the first derivative changes from increasing to decreasing, or what I tell my students is where the first derivative has an extremum. And I think that's the fastest way to justify point of inflection on the AP exam. Talk about extreme values of the first derivative, because you use the fewest words and you want to earn points fast on this exam. So where does g prime have an extremum? So I'm going to just quickly go back here. My graph of g prime is right here. In fact, I don't even have to worry about the x-axis where it is if I'm thinking about this problem, because I just need extrema. And so the extrema on g prime occur at x equals 0 and at x equals 7. So that's how you would answer this question. X equals 0 and x equals 7 because g prime has extrema there. Okay. And then what is the average rate of change of h on this interval? Well, this is a pretty straightforward question. It leads into the next one. It's h of 2 minus h of -2 over 2 minus -2. By the way, notice it asks for average rate of change, not average value. Those are two things that are really easy to confuse. Some students have a hard time with that. They confuse average value and the average rate of change because they're just about the only places that you see the word average in AP calculus. And so students often will think the answer is the other when it's supposed to be the one. So that is the average rate of change. And I think if you look at the graph of h, that's a simple question to answer. I think h was actually, that piece of h was symmetric over the x-axis. This winds up being 0. Look at part F. There is no number c between -2 and 2, the values we just found the average rate of change over, such that f prime of c is equal to 0, the number we just computed. Why does this fact not contradict the mean value theorem? Well, to answer that, you have to know what the hypothesis of the mean value theorem is. One of the parts of that hypothesis, the two parts are that the function that we're investigating is both continuous on the closed interval from -2 to 2 and differentiable on the open interval from -2 to 2. And this function, h, is not differentiable at x equals 0. Okay, you have this sharp corner point. If you did one-sided actually either one-sided quotient would not exist. It would approach infinity because the change in x is going to be going to 0. At any rate, the so we don't violate the we don't violate the mean value theorem because we don't meet the hypothesis of the mean value theorem. That does not contradict the mean value theorem because f is not differentiable at x equals 0, which is in this interval -2 to 2. That's part of the hypothesis of the mean value theorem. Then the last part of this is asked for the second degree Taylor polynomial for G centered at x equals 8. So to answer a question like this, I think the right thing to do is to know in advance, have in your notes ready for the exam, the general form for a Taylor polynomial for any function centered at any point. And simply being able to type into kind of a template is a simple way to answer a question like this. So this polynomial is g of 8 plus g prime of 8 times x minus 8 plus g double prime of 8 over 2 factorial times x minus 8 squared. Okay. Then what you have to do is look up, calculate what each one of these numbers is. So you have to go back to the graph probably to get g of 8 being 8 plus the integral from 5 to 8. So g of 8 is 8 plus, let's see, the area of this triangle, 1, 2, 3 by 2, looks like the area is 3 and it's a negative, right? If I did that right. So -3 plus 8 sounds like 5. So g of 8 is going to be 5. Then we need g prime of 8. So we go back to the graph. G prime of 8 is the same as, let's see, it's g prime of 8 is 1 plus h of 8. And h of 8 looks like it's right there, 0. So 1 plus 0 is 1. So g prime of 8 is 1 times x minus 8. And if I make a mistake, please holler at me, okay? Because I'm not immune. I'm not perfect. I'm not immune to making mistakes. Then we need the second derivative of g at 8. Well, the second derivative of g any place is g double prime. So g double prime of x is h prime of x. So I need the derivative of h at 8. I need the slope of this line over here, and that looks like it's 2. And so g double prime of 8 is going to be 2. And so we're going to get 2 over 2 factorial. You could simplify that, I suppose, x minus 8 squared. And that's your answer. You can leave it just like that and get full credit. Okay. Any questions, please type them into the chat if you have any question about any of that. The rest of the time that we have about, looks like 15 minutes left, which is time for us to look at highlights from these next few questions that I have ready for you. So this problem 2 focuses quite a bit on Taylor polynomials. This is just another way to ask a question about a Taylor polynomial that's just backwards from what we just did. What we just did was to build a Taylor polynomial frontwards. We had information about a function and induced the Taylor polynomial. The other way to ask a question about Taylor polynomials is to hand you the Taylor polynomial and ask you questions about the function that produced that Taylor polynomial. For example, I could ask you what g of pi was. Well, you could just plug it into the Taylor polynomial to get g of pi. G of pi is -1. It's the constant part of the Taylor polynomial, the part that doesn't have the term that doesn't have an x in it. And of course, you need g of pi to get this tangent line that I asked you for in part A. And then you need g prime of pi. And if you look close at that polynomial, you'll notice that term with an x in it. And so the coefficient of x has to be 0 in this Taylor polynomial, which tells you that g prime of pi, sorry about the chicken scratch here, g prime of pi, I'll try to do better this time, is 0. And so what's an equation for the tangent line? It's very similar to that one that we did. It's a constant function, y equals -1. Okay. So then part B of this problem asks whether G has a max, a min, or neither at pi, and explain your reasoning. If it's not possible to determine whether you have a max or a min, explain why not. The reason I ask about max or min is because we know that we have a derivative at pi 0. So maybe we have a max or a min, or maybe neither. So what other information would tell us? Because we don't know from what's in front of us whether the first derivative changes from positive to negative or negative to positive, but we do know what g double prime of pi is. If you know how this Taylor polynomial is constructed, what g double prime of pi is the thing that produced that 9 right there. Because 9 times x minus 2 squared over 2 factorial. So if the second derivative is positive, where that means my curve is concave up, and it's concave up at a point where the tangent line is horizontal. This is testing the second derivative test. Okay, so g double prime is greater than 0, g prime of pi is equal to 0. Therefore, and 3 dots are good for therefore, I have a max. And what I have written right here would get full credit for this question. Okay. Any questions? Again, please feel free to type to the chat. Okay. I think what I'd like to do here, because this question C here is really a tricky question, and the solution again is in the solutions packet. So rather than spend a time going through the trickiness of this, I'd rather do a more broad exploration of different types of problems than focusing so tightly on one little bit that's really kind of tricky. So I'm gonna abandon this question and march forward to another question, unless I see that there's some questions in the chat about what we've done so far on this question. By the way, this part E at the bottom, identifying F, G, or H with an explicit formula. I had in mind a fun when I wrote this Taylor polynomial to begin with. I had something up my sleeve, so to speak, and I asked you to identify what was up my sleeve when you got to part E, but it turns out that part E couldn't be asked this year because it involves identifying a particular Maclaurin polynomial. I think these things involve either a cosine or a sine function, one or the other. And so since they involve a Maclaurin polynomial and that's not tested material, identification of those particular ones, we couldn't ask the question here that's asked in part E. We excluded that content from the exam this year. So here's another question. I feel like I've given you enough time to ask anything. The solution for this one, you can actually see, I put the solutions here in this presentation. So there's some of those answers. I'm going to quickly leave that so if your teacher wants to ask you that question, they can still ask you that question on an exam. So here's another way to ask a question that's just this like massively tabular problem. And I made this question up just so that you could see, excuse me, the kind of ways that we could ask questions about integrals and derivatives when we can't ask questions about specific functions. So this is what you do if you want to still test, do students know the chain rule? Do students know the product rule? Do students know how to find the derivative of an inverse? Those are questions A, B, and C that you're looking at right here. You have to know how to do those things to answer those questions. And you can answer those questions because the values that you would need are in this table. Okay, so let me just do one of these as a for example, and maybe the hard one here maybe for you would be question C. How do I do the derivative of K, which is capital F inverse of T, or sorry, F inverse of T, the inverse of, oh, this is a typo. So this should say the capital F is the inverse of F, not of H. Unless I let's see, can we find the derivative of f inverse at x equals 1. So yes, we can, because we know what f of 1 is. So we know what k of 1 is, okay? So k of 1 is f inverse of 1, which is 1/4, okay? So if we want to find k prime, that's 1 over f prime at f inverse of 1. And f inverse of 1 is 1/4. So 1 over f prime at 1/4. And f prime of 1/4 we can find right here is 1/2. So we get 1 over 1/2, or 2. So this is a little bit tricky. The reason they introduced this other function k, you might be more familiar, it might make more sense to you if I had written this. What's f inverse prime at 1? It's 1 over f prime at f inverse of 1. And I'd actually prefer to use this other notation. It's a little clunky because you need these extra parentheses around f inverse, but that's how you do that problem. I just wanted to illustrate that we could test the inverse rule, the derivative of the inverse rule, using a table. We can test the product rule, as it's done in part B here, using a table. We can test the chain rule, as done in A, using a table. We can test the fundamental theorem and U substitution using a function like is done here in question D. We can test midpoint sums. And if you look down here at the bottom, we can even test, do you know how to do integration by parts? Okay, so to do this one, I think this last one, you would set U equal to T and dV equal to capital F prime of T. Because then you can find du being dt, and you can find v is capital F of T. Then you're going to kind of plug and chug after that point. This integral of u dv is uv tf of t minus the integral of v f of t du, which is dt. And check it out. I tell you what, and this thing also has to be evaluated from 0 to 1. And I tell you to evaluate this integral in terms of k. Well, this integral from 0 to 1 note is given as k. So what you have to do is evaluate this first part and then subtract k. And that's the answer to that question. So this TF of T you can get by looking up in this table up there from 0 to 1. And I'll spare you going through the details of that again. It's in the solutions packet. Okay. So let's see. Do we have time enough, Aaron, for take a quick look at maybe one more question?
Oh, sure.
Okay. Let me scroll down quick and get to one more. Let's see. So this problem comes to us courtesy of these two rock stars in AP Calculus YouTube Live fame, Brian Passwater and Tony Record, who are doing a marvelous job with these YouTube Live sessions. If you're not looking at some of these sessions these guys are doing, then you're missing something. And I know everybody's stressed, and I'm not trying to say you're a bad person if you're not looking at those things, but I'm trying to point out is these things really do have great value. These guys are doing very good work preparing and writing questions just for you. So I stole one of their problems to do here just to illustrate another, just because it's kind of slick and it illustrates some cool ideas. What we have here is a twice differentiable function f made up of these three kinds of pieces. Okay, so they give you the graph of f prime here, and they tell you that the graph of f prime really has three pieces to it. It has this linear piece from 1 up to 6, and then the rest of it is sort of what you're looking at. Then they give you this other function h, really simple. It's 2x minus 5. It's this other linear function, 2x minus 5. And check out what's going on in part A of this question. These guys are doing a similar thing to what I just told you, except they're not doing it with a massive table. excuse me, instead, what they're doing is and they also told you, notice that f of 3 is 7. That's going to turn out to be important information because you're asked for g prime of 2. Notice that's going to involve f of 3 after you use your product rule. They're testing the product rule and the chain rule, and can you use a graph to read data off of in order to get information about a function value and a derivative value. It's really a slick question that tests a lot of calculus in a relatively compact and relatively simple kind of. We got the product rule, the chain rule, a graphic presentation, knowing that a derivative of a line is coming from the slope of a line. All of that stuff is in this question. Again, I'm not going to go through the details of the answer. I mostly wanted to point to this question to show you the kind of things that you might see. Here they ask you to integrate from 2 to 4 f prime of h. So when you see something like that, the integral of f prime of something, you should be sort of leaping at the fundamental theorem. And that's what this is testing. It's testing the fundamental theorem along with u substitution, because notice that h is just linear. In fact, the first thing you really want to do in this problem is replace h with 2x minus 5. And that'll get you started on the right path to do a problem just like this. And then they also have one where they have a test on integration by parts. This is very similar to the one that I wrote in that problem that we just looked at, or at least one of the previous problems that we looked at, where you can test integration by parts with these general functions. And typically when that's done, one piece of that integration by parts in context like this has to involve a derivative, because you have this dv, right, that you need to assign to one of the factors in that integrand. dv better be a derivative so that you can integrate it, okay? So be looking for something like that. If you see a product involving a derivative with some other, chances are, and they're asking you to evaluate an integral, chances are really good they're talking about integration by parts, okay? Let's see, do we have time? Yeah, we have a minute or two. Let's look at the last couple of parts of this. This guy here, I actually told either Tony or Brian Brian that I thought that they were stretching this a little bit. This question actually involves partial fractions, and I think they kind of they were forcing this a little bit. Once you wind up substituting for this denominator here, you wind up with an old machine, and I don't think you're going to see a question that can be done with a machine on the exam. Producing that denominator, maybe that could be asked, because finding f prime of x on the interval from 1 to 2 could be an important thing to be able to do. I think F might have been part of that linear piece that you could write an equation for that line. So a lot of algebra in this question, part D. And then you'll notice what they did. It's very similar to what I did about finding a third degree Taylor polynomial down for this other function. They did it with k prime being f of x plus 2. So that was kind of a slick way. You got to do a translation, and you also have k prime. So you know that k of 1 is -1. That's given. And so you can kind of plug and chug again to pull those things together. So, phew, I know I'm exhausted. I imagine that you all are pretty exhausted too. This has been fun for me, though. It always helps me to do this stuff, and I wish you all the best. Be good to yourselves over the next few weeks, as your next couple of weeks, really. Time is bearing down on us ready for this exam. There isn't that much time left. But I do wish you all the best, and thanks a lot for joining us today. My email, I think, is out there someplace. Feel free to send me emails if you have questions about this presentation, or if any of the teachers have any questions about or thoughts about the exam, please feel free to contact me with that. And I do reply to those kinds of questions. I had a blast here, Aaron, over this session and the previous session. I'm going to turn it back to you now.
All right, thanks, Mark. We certainly appreciate you taking the time to work with us here. So I'm sure everybody who's tuning in was very grateful. So let me share my screen here. All right, so if you have questions, like Mark said, for him or for Michael or myself, feel free to reach out to us. If you are a teacher and would like the solution handout, feel free to email us and we will get that for you. The link there is kyap2020.com. Today's recording will be posted there by the end of the day. And next week, we've added one additional review session on May 7th at 2 p.m. time. Nothing but AP exam preparation. So a lot of what Mark was talking about, but even more of it. No, too much can't hurt. And we'll be joined by Amy Cash, who is a consultant for the National Math and Science Initiative, as well as an experienced AP Calculus teacher at Bowling Green High School in Kentucky. So Mark, Michael, if you don't have any other comments, we'll go ahead and sign off, and hope to see you all next week. All right. Take care. See you all later.
Bye-bye.